What exactly makes forging so special? Forging exploits a unique feature of our industrial metals, their plasticity. For more than 2 million years, mankind had to rely on stones, a subset of minerals in general, as its main tool material. Stones cannot be deformed, they break and splinter. In stark contrast to this, industrial metals can sustain substantial deformations without breaking. In order to understand this difference, you have to go deep down to the level of the atoms. In nature, most solid substances belong to a world of crystals. All their atoms are lined up in perfect order and symmetry along a set of straight lattice lines. This rule holds for minerals just as well as for metals. The microscope will reveal that what we normally perceive as a monolithic body really consists of a disordered conglomerate of tightly intertwined crystallites. These have grown towards each other from all possible directions until their boundaries met. In most minerals, these crystallites consist of different atom types that have previously exchanged electrons. They thus feature either a positive or negative electric charge. Just as in the case with magnets, different charges will attract each other while identical charges will be repelled. Every atom will thus associate with neighbors of opposite charge. If this order is disturbed by mechanical deformation, atoms of identical charge will become forced neighbors. Attraction will revert to repulsion and the crystal disintegrates. In stark contrast to this, metal atoms are able to set their outer electrons free to wander around through the lattice. A metal crystal is thus formed by atoms that all exhibit a positive charge, yet they will not repel each other, but rather hold together because the space between them is filled with mobile electrons having the opposite charge. Since they are electrically attracted from all sides, they will bond the crystal structure together. In such a crystal, neighboring atoms can be moved past each other without provoking repulsion. This is the secret of the plasticity of our metals. Steel is not a uniform material. The differences between individual steel grades are sometimes enormous. To verify this, we load steel wires with an identical cross-section of 1 square millimeter each with weights. Both materials are unalloyed except for a slightly higher carbon content of the second wire. The first specimen is a soft material suited for uses such as florist's wire. To achieve this, it was heat-treated at high temperature followed by a slow cooling process. This made it soft. The wire already fails when subjected to a load of just 32 kilograms. The second test is performed with a high-strength spring steel wire. In anticipation of its superior strength, the rod for the application of the weights had to be fitted with an additional base load of 27 kilograms. The high strength of this wire is mainly achieved by cold work hardening, caused by the strong deformation of the material during the drawing of the wire at room temperature. This high-strength wire fails only after being loaded with a total weight of 162 kilograms. This is about 5 times higher than for the first specimen. In the past, forging was heavy labor. Nevertheless, people undertook this grind because it significantly improved the value of the metal that had been previously melted and cast. A raw cast ingot is not ready for use. It is beset with numerous defects, such as gas pores, shrinkage cavities, slags, and precipitations. It needs a refining treatment by forging or rolling, which will decisively improve its properties because the material is intensively compressed and sometimes even literally kneaded. Gas pores, as well as shrinkage cavities, are collapsed and their inner walls welded together. Impurities and inclusions such as slag and non-metallic precipitations are broken up, reduced in size, and dispersed. This neutralizes any negative impact on the mechanical properties of the forged part. In the case of steels, there is a special effect. Hot forging leads to full-scale recrystallization, i.e., the transition from old crystals to new, very small crystallites that can only be seen at high magnification. In combination with sustainable heat treatment, this can be used to significantly improve strength and toughness. Furthermore, the forging process creates a fiber structure within the part, significantly enhancing its load limit in the direction of the flow lines of the material. Cold forging, too, will result in changes to the crystal lattice, resulting in greatly enhanced strength and hardness. In addition, cold or medium temperature formed parts excel by virtue of their outstanding precision and surface quality, so they can often be put to use without subsequent machining.
My name is Daniel.
I'm 18 years old and I'm an apprentice tool and die maker.
Hey Daniel.
Hi Daniel, all clear with you? May I have a look at what you're doing here right now? I'm currently working on the 3-axis milling machine from Maho. The part that I'm currently working on is the test piece for our midterm exam. Wow, this looks pretty intricate. Indeed, but it's not as difficult as it seems at first glance. With time and taking a closer look, it turns out to be rather easy. I will machine this workpiece using the milling machine. Its movements along 3 axes, Z-axis, X-axis, and Y-axis, enable me to produce the part. First, I have to look at the different tools. I key in their specific data on the control system. Afterwards, I write the required milling program. This is performed by entering instructions specifying movements. Finally, I only have to push start, and the machine will process the individual code lines and thus produce the part. The knack consists of conceiving a suited strategy in your mind. Afterwards, the machine will do everything automatically.
Hello,
my name is Martin. I'm an apprentice industrial mechanic with Buderus Edelstahl in Wetzlar and currently in my 3rd year of instruction. Why did you opt for this career instead of looking for an office job? The tasks of an industrial mechanic are diversified and won't become boring. As long as machines are needed to produce goods, hands will be required that know how to service them.
Hi,
my name is Sven. I'm an apprentice metal cutting mechanic and currently in my 4th year of instruction. My master has just given me this blueprint and asked me to produce this part for him. I've already chucked the part. As soon as the machine starts, the lathe tool will move towards the workpiece, the lathe chuck will start turning, and the part will be produced.